All right. So today we are going to go over the questions in quiz 5. Um, and I'm going to try to do this in the real time, and also we can discuss the concepts behind each and every question. Okay, let's give this a shot. Okay, so questions together. All right, question number 1. Calculate the pH of an aqueous solution that contains 0.004 molar concentration of a certain acid. All right, so you're given the initial concentration of the acid and also the pKa, right? And then you also calculate the pH. Now, for a weak acid, we know the H3O plus concentration, H3O plus concentration is equal to the initial concentration, C naught, times Ka, okay, the square root of this. Okay, now what we need to do is we need to plug and chop the numbers. C naught is 0.004, and then Ka is 10 to the power of minus 4.5, because the Ka is 10 to the power of minus pKa. And then since the pKa is 4.5, the Ka must be 10 to the power of minus 4.5. And then what we need to do is we need to take the square root of this entire thing. Okay. Now, if you use a calculator, all right, so what we have here is 4 times 10 to the power of minus 7.5. Okay. And if we take the square root of this, you should get 2 times 10 to the power of minus so 7.5 divided by 2 should be 3.75. 3.75. So this should be H3O plus concentration. Now, once we have this, what we need to do is we need to take the minus log of this to convert this to pH, because pH is minus log H3O plus concentration. Now, for pH must be equal to minus log H3O plus concentration, which is 2 times 10 to the power of minus 3.75. Okay. Let's see if I can do it somewhere. I use a calculator. It's an online calculator. Right? So if I take minus log 2 times, this is the first time I'm using this, 10 to the power of minus, it might be easier to do it here actually. Okay. Minus log 2 times 10 to the power of minus 3.75 is 3.44897. Right, so let me go back to It says 3.48. Yeah, 3.448. Point 448. Say 3.45. I'm going to reach that answer. Yep, so that's question number 1. And then let's move on to question 2. Calculate the pH of an aqueous solution that contains 0.01 molar concentration of a certain base. Now, previous one was an acid, okay? This one is about a base, okay? Now, when it comes to the bases, it's the same thing, but what we have is the OH minus concentration, right? So the OH minus concentration here, OH minus concentration is equal to C naught, which is this right over here. This is my C naught. Okay, I'm going to write 10 to the power of -3. Okay, multiplied by the KB, which is 10 to the power of minus 5.5. Okay, and then we have to take the square root of this entire thing. Right, if you do this, this is 10 to the power of minus 8.5, right, divided by 2, which is 10 to the power of minus 4.25, right? So that's the OH minus concentration. Then what we can do is we can calculate pure OH from that, which is the minus log of OH minus concentration. Okay, pure OH is minus log OH minus concentration. Okay, this should be equal to minus log 10 to the power of minus 4.25, which is 4.25. Okay. Now we have pH. You know that at 25 degrees Celsius, pH plus pOH is equal to 14. Therefore, pH is equal to 14 minus 4.25, which is 9.75. 9.75. So I'm going to type in that answer here. It's 9.75. 9.75. Okay. That's question number 2. Moving on to question number 3. The certain weak acid has a Ka value of this. What would be the value of the pKb of this conjugate base? Okay. Okay, this is again another straightforward one. The idea is for conjugate pairs, pKa plus pKb is equal to 14. okay? And therefore, the pKb is equal to 14 minus pKa. And we define the pKa of pKa using the Ka value, which is this is the Ka value. And I'm going to use the Google calculator. 3.6 times 10 to the power of minus 7. If you go to the Google calculator, 3.6 times 10 to the power of minus 7 in minus log 3.6 times 10 to the power of minus 7 is equal to 6.44. Right? So pKa is 6.44. Let's go back to our question. Okay, and now therefore the pKb must be equal to 14 minus 6.44, which is going to be 7.56. Type that answer here. 7.5. Right, that's question 3. And question 4. And calculate the pH of an aqueous solution that contains this concentration of NaOH. Okay. Now again, we are given the given a strong base. Okay, strong base provides OH minus ions to the solution. It's gonna generate OH minus ions. Right? Yeah, and then it's gonna be a complete dissociation. Therefore, the initial concentration of the base is equal to the OH minus concentration. Okay, therefore OH minus concentration is equal to 9 times 10 to the power of minus 4. Okay, and from this we can calculate the pOH. Now for pOH is equal to minus log the OH minus concentration, which is 9 times 10 to the power of minus 4. Okay, let me use the Google calculator one more time. 9 times 10 to the power of minus 4 minus log 9 times to the power of minus 4 is 3.045. Okay, so let's start that time. 3.045. 3.045. Okay, that's going to be our pOH. Right, and we know pH plus pOH is 14 at 25 degrees Celsius. Now for pH is 14 minus pOH, which is 3.045. Okay, I'm just going to come out to the 10.9. I'll go with a rough value 96. That's about 10.96. Okay, going back to the question 4. I'm going to that. I'm going to enter 10.96. Check the answers later. Right. So let me clear my screen. And okay. Now let's move on to question 5. An aqueous solution containing 0.002 molar concentration of a weak acid has a pH of 6. Calculate the pKa of this acid. Okay, now this is the other way around. You are given the pH, and also you are given the initial concentration. You also find the Ka, pKa. Right? Now, since you know the pH, right? We know the pH is equal to minus log H3O plus concentration. Okay, we can calculate the H3O plus concentration. Now for H3O plus concentration is 10 to the power of minus pH. The power of minus pH, which is 6. The power of minus 6. Okay, and also we know for a weak acid, H3O plus concentration is equal to C naught times Ka, the square root of the entire thing. Right? And then therefore we know we can say that this. No, we can say that C naught times Ka is equal to 10 to the power of minus 6 squared, right, which is 10 to the power of minus 12. Right? And therefore, Ka is equal to 10 to the power of minus 12 divided by the C naught. By C naught. Okay, by C naught. Okay, I'm going to rewrite that. And then I'm gonna plug in the value for the C naught now. 10 to the power of minus 12 divided by C naught is 2 times 10 to the power of minus 3. Okay, this value over here, 0.002. Okay, now this is equal to let's say 1/2 times 10 to the power of minus 9. Should be 5 times 10 to the power of minus 10. Right? You should check the calculation actually. Again, just to make sure everybody can follow me, I'm going to do this again. Going to Google Calculator. What I did was I just divided 10 to the power of minus 12 by 0.002. Okay, and that gives me 5 times 10 to the power of minus 10. This value over here, and that's what I have here as my answer for the Ka. Now going back to the question, now that's the Ka, but what I need is the pKa. Okay, and then again, pKa is minus log of Ka. Ka is the minus log of the Ka value, which is 5 times 10 to the power of minus 10. Okay, which give me a 9 point something. So let's do this here on Google Calculator. The minus log 5 times 10 to the power of minus 10 is 9.3. Okay, this value over here. 3. Going back to this, I'm gonna type in 9.3, and that's my answer for question 5. Okay, I'm gonna clear this again. I'm gonna move on to question 6. All right, question 6 tells us dissolving a certain weak acid in water makes a solution that has a pH of 5.7. Okay, and so far so good. At 25 degrees Celsius, what would happen to equilibrium of this aqueous solution if more HA was added to the system? All right. Now, only thing that matters to us is we have an equilibrium now, okay? And that equilibrium is when HA reacts with water. Aqueous, this is a physical Q, reacts with water, H2O, liquid. Okay, we're going to have this equilibrium in the system. We're going to have H3O plus generated. Plus A minus. Okay, now what we're going to do is we're going to use the kinetic argument or kinetic perspective to explain what's going to happen to the equilibrium when we add HA to the system. Okay, now we know in the kinetic argument what we do is we look at the forward rate and the reverse rate. Okay, so let me call rate forward. Rate forward must be equal to rate constant for the forward reaction times HA concentration. Okay, HA concentration, and then rate reverse, rate backwards should be equal to rate constant for the reverse reaction times, we have two species that two concentrations now. We have H3O plus concentration, and we have the A minus. Okay, and what we do is we add HA. Okay, when we add HA, it will increase the HA concentration. So on the HA concentration is in the forward rate. Okay, so therefore adding HA will increase HA concentration, and in turn it will increase the forward rate. Okay, the forward rate is going to be greater than the reverse rate. Therefore, option A is out and option D is out, because we know the forward rate must be greater than the reverse rate. If we have a greater forward rate than the reverse rate, that means the forward reaction is gonna occur more, producing more products. Therefore, the equilibrium should shift towards the products. Okay, and then the only answer that reflects that is option C. Forward rate is greater than the reverse rate, and the equilibrium will shift towards the products. Okay, so the correct answer is C. Let me select the answer maybe. Here we go. Now, moving on to question 7. So we have, again, it's a kinetic perspective. What would happen to the above equilibrium when NaOH is added to the system? NaOH, remember, is a strong base. It's going to provide OH minus signs. That means you are adding this guy over here, right? So again, what we need to do is we need to write the forward rate and the reverse rate. Okay, in this case, the forward rate is rate constant for the forward reaction times CH3 2 times and NH, right? That is the forward rate. And when it comes to the reverse rate, you're going to have more species now. It's going to have the rate constant for the reverse reaction, okay? And then the conjugate acid. So this is CH3 twice NH2 because it has accepted the proton now. NH2 plus concentration times OH minus concentration. Okay. Now, when this happens, let me go back to my pen. All right, you are adding OH minus, therefore you are increasing the OH minus concentration. That's the perturbation. Okay, OH minus only appears in the reverse rate, and therefore it will increase the reverse reaction rate. And if the reverse reaction rate, therefore, it must be uh, so the first two options are out for that reason, right? It must be between C and D. And between C and D, if the reverse rate is greater than the forward rate, then new reactants must be formed. And then that is reflected in option D. Now, I would select option D as the correct answer for this question. Right. Moving on to question 8. Given the KB of the reaction, select all the species that act as bases. Okay. And then we know this is a base. Okay. The reason is we know anything that reacts with water and produces OH minus ion is a base. Okay, so this is a base. And also we can see that we have a nitrogen with a lone pair here that can abstract a proton from H2O, which makes it a base. Okay. Great. Anyway, now for that reason, we can say that this definitely is a base. It is accepting a proton from H2O. Okay. And also on the other hand, the only species that can act as a base is OH minus. Okay, OH minus can accept a H plus ion, okay, which makes it a base. Okay, and then when it comes to the other guy over here, this is called the conjugate acid. The conjugate acid cannot accept a proton now, positively charged proton now, because it already has a positive charge. Okay, positive charges will repel each other. Therefore, it is more likely that OH minus accepts proton in a acid base. Right, so the correct answers are these two. Therefore, I think is option B. That's what I will select as the correct answer for this question. Okay, moving on to question 9. Let's see. Given the KB of reaction, select all the species that can act as acids. I think it's the same reaction as before when they are asking for the acids, right? And then since H2O is donating a proton, H2O is acting as an acid. And also on the other hand, the positively charged conjugate acid is obviously the other acid. Therefore, the correct answer must be option D. option D. Okay, moving on to the last question. Okay, we already did a KB calculation before, but okay, we can do that again. We're given the PKB. We also find the KA value. Right. Once again, we know that pKa plus pKb is equal to 14 for conjugate pairs at 25 degrees Celsius. Right. Therefore, pKa must be 14 minus 4.2, which is 9.8. Okay. Now Ka must be 10 to the power of minus 9.8. Right? This should give us 10 to the power of minus 10 answer. The only 10 to the power of minus 10 answer is the last option, option D. I'm going to select option D. That's my correct answer for the question. Right. Those are all the questions we had in quiz 5. Okay. Oh, let's submit this and see if it will agree with my answers. And once you press submit, okay, submit this. Right, apparently it will agree with our answers. So now 100% go. All right. Okay, I'll see you next time. Bye, everybody.